So for this next video in 10.5, we're going to look at what we're calling the limit comparison test. It's our second comparison test. I'm going to pick up where I left off, so you'll see everything here already. We were examining the summation of n minus 1 squared, and that was our a sub n. And we said, well, that's easily compared to the summation of 1 over n squared because the n just has a difference of 1, right? So we're going to let that be our b to the n, which we know is a p series. The p is greater than p of 2 is greater than 1. So we know b sub n definitely converges. The problem was when we continued our direct comparison test, we found, yeah, but for us to say that a sub n also converges, a sub n has to be less than b sub n. But since a sub n, when you compare them, has the smaller denominator, it is actually larger than b sub n. And you can see on this graph here, wherever b sub n falls, a sub n is always going to fall a little bit above it. So what happens is our direct comparison is inconclusive. Now, it doesn't mean the opposite. Because we can't say a sub n converges does not necessarily mean we can say it diverges. You got to be careful there. We just say, oh, we can't use that test. That test is inconclusive. Fortunately, I have so many other tests to try. So thinking about it, we're like, maybe it's close enough though. So what does that mean? If we can determine that a sub n is behaving the same as b sub n, meaning, well, b sub n's converging. If we can find out that a sub n's behaving just like it, then we can determine it too is converging. How do we do that? We do that using what we call a limit comparison test. So we're going to call comparison test, and we'll call this one an LCT. LCT is great when the DC test is inconclusive, so there's two times. Yes, when it's inconclusive. It's also great, as you'll see in one example. We've done, when we were doing direct comparison tests, we've done these two series that are very easy to compare. It's not always easy to compare to determine which one's bigger or smaller. So with the limit comparison test, doesn't matter which one's bigger or smaller. We're just looking, do they behave the same? In other words, are they growing at the same rate? And if we can determine they're growing at the same rate, we're good to go. So how does my limit comparison test work? Again, we have a given a sub n that we are going to compare to a known b sub n. When I say known b sub n, you pick b sub n. You pick b sub n based on series you know, like 1 over n squared, a geometric, something that you're very familiar with. Here's how the test works. If the limit as n goes to infinity of the ratio of a sub n and b sub n, and here's a nice little thing. It doesn't matter what the ratio looks like. It does not matter the order, meaning you could also do b sub n over a sub n. All right, so don't get caught up. It has to be one or the other. It doesn't. You're just looking at the ratio of the two. Equals L, where L is a positive finite value. So what do I mean by a positive finite value? L is greater than 0 but less than infinity. What that means is you cannot get 0 or infinity. Let's make that clearer. Not 0 or infinity. As long as you get a value that's not 0 or infinity, or any negative number, as long as you get a positive value that's not 0 or infinity, then we can say a to the n and b to the n grow at same rate, meaning they either both converge or both diverge. So whatever your known b sub n is doing, you can then state that a sub n is doing the exact same thing. Remember, it just can't be 0 or infinity. Because think about it. When you're taking the limit of a ratio and you get 0, that means your denominator is growing at a much faster rate than your numerator. If you get infinity, that means your numerator is growing at a so much faster rate. As long as you don't get 0 or infinity, you can actually state they're growing at the same rate. So if one's converging, the other is also converging. So how does this work? Let's go back to the one we were working with, which I believe was n minus, right? Yeah, n minus 1 squared. So we have the summation of 2 to infinity. Did I put 1 up here? Nope, I didn't even put anything. That's fine. The summation of 2 to the infinity of 1 over n minus 1 squared. That's my a sub n. I'm going to compare it to b sub n, which is a summation of 1 over n squared from 2 to infinity. Again, to do this comparison, you need to know what b sub n is doing, so we might as well finish that off real quick. We know b sub n because it is a p series, and p is greater than 1, it converges. So before you do anything, just make sure you know what b sub n is actually doing. Now, the comparison, a little bit more complicated than direct comparison. We need to take the limit as n goes to infinity. And again, it doesn't matter what you put on top and bottom, so don't worry about that. All right. And you're going to see what happens real quick with this crazy fraction. In this case, we're dealing with these two ratios, and we can actually, division of a fraction means multiplication of its reciprocal, right? So isn't that the same as the limit as n goes to infinity of 1 over n minus 1 squared times n squared over 1, right? You'll get in the habit where you won't even have to write the big fraction. You'll just start writing it as times the reciprocal instead of the ratio. And let's go ahead and do this to make this a little bit easier for ourselves. Instead of n squared minus 1, if it makes you feel better, you can do n squared minus 2n plus 1. Okay? So again, I'll clean this up. And it's n squared over n squared minus 2n plus 1. You have worked enough with limits now. If not, you can L'Hopital this twice, because if you L'Hopital it the first time, you're going to get 2n over 2n minus 2. You L'Hopital it a second time, and you see right away that you get 2 over 2. Or you can just use your coefficient rule, because these are the same. Coefficient over coefficient. No matter which way you take that limit, you get a 1. Okay? And 1 is perfectly legitimate. It is a positive, right? Yep, we're good. 1 is a positive finite value. So, what we then state is, since we already know b sub n converges, by the limit comparison test, my LCT test, you can call it LCT. And what did we use for b sub n? We used our p-series test. I keep wanting to put an E before S and p-series. A sub n converges. Good. All right. Again, you only need to write that as long as you show me all the other steps above. Okay. So let's take a look at probably 2 more of these so we can get a good idea of how they work. Next example. Let's do the summation of 1 to infinity of square root of n over n squared plus 1. I picked this one a little not quite as obvious, right? So we have our a sub n. We need a b sub n. Here's what you want to remember when you're trying to determine that b sub n. What is the insignificant value of this particular series as you go to infinity? What becomes kind of, you can ignore? Well, as we go to infinity, does the plus 1 really matter? It does not. So I can compare it to a series that doesn't have the plus 1. Well, what is that series? 1 to infinity, that's n to the 1/2 over n squared. Well, we know how to work with exponents. 1/2 minus 2 is not 1, and it's negative 3/2, so n to the 3/2 from 1 to infinity. Here is my b sub n. So let's finish up and talk about b sub n, why we are on b sub n. Well, that's just a p series, right? Yep, did it again. I know. That's p series. What's p equal to? P is 3/2. Well, 3/2 is greater than 1. So that particular p series will, of course, converge. All right, so we have a b sub n. We feel good about our b sub n. We got rid of our insignificant plus 1 to get our b sub n series, and we know b sub n converges. What we need to do now is compare the series. Do they behave the same? So remember, when you're doing a limit comparison test, that's what you're determining. Do these series grow at the same rate? So I'm going to take the limit as n goes to infinity. I'm not going to write this as a big fraction because remember, I'm taking this series with now this series. Okay. Instead of writing it out as a big complex fraction, I'm going to do the multiplication of the reciprocal. So that's going to give me what? Square root of n over n squared plus 1 times n to the 3/2 over 1, right? This was my a sub n part, and that's the reciprocal of my b sub n part. Reciprocal of b sub n. Okay. All right, let's clean this up a little bit and get this into something we can work with. Well, the first part, n square root of n is just n to the 1/2, right? Isn't that just n to the 1/2? N to the 1/2 times n to the 3/2, you add up your exponents, you get n to the 4/2, so that is simply n squared. Over n squared plus 1 times 1 over n squared plus 1. And yep, yeah, you don't need it. You got this. It's 1. Okay, L'Hopital twice, whatever you need to do, it's 1. Okay, just coincidence that both limits came out to 1. So again, 1 is a positive finite number. So yes, we can say a sub n converges by limit comparison test n p series. Okay? And again, you can be that brief as long as you showed me above the work that I just did. If you're not going to take the time to show the work, you need to be a little more detailed in that last statement. Okay, let's do one more of these, and then we'll move on. Summation. Oh, here we go. N times 2 to the n over 4n cubed plus 1 from 1 to infinity. Okay, so let's go ahead and try to determine a b sub n. Because when you start these, even with the one above, by the way, when you start these, you're finding like, wait, this looks a lot like another series that I can work with. That's the comparison part. Whether you do a direct or a limit, you can always try the direct first and see if it's inconclusive, in which case you have to do a limit. Or you get to a point where you can't do a direct comparison because, quite honestly, how do you know if square root of n over n squared plus 1 is bigger or smaller than 1 over n to the 3/2? If you can't easily do that comparison, you've got to just do the limit test, and the limit test becomes much easier to do. The direct comparison test you can always try first with more simpler series where it's kind of easier to make that direct comparison to say, oh yeah, this one's definitely always bigger than this one or smaller. So for this one, let's think through this. First of all, I'm going to ask again, what is insignificant as you move off into infinity? Okay. What becomes insignificant? What becomes insignificant? That plus 1, right? That's not going to make a difference. So let's start with saying, well, b sub n is going to be, I need my n, I need my 2 to the n, I need my 4n cubed. I don't need the plus 1. Well, wait a minute. I can simplify that because I have an n over an n cubed. So wouldn't that simplify to 2 to the n over 4n squared? And even at this point, I would say that 4 is even insignificant. So this is what you're really comparing it to. N to the 4th over n squared, 2 to the n over n squared. So that's the series you're comparing it to. So b to the n simply becomes 2 to the n over n squared. Okay, so again, before we even make our comparison, we have to determine, we can figure out what's happening with our b to the n we just came up with to compare it to. So we got to finish playing with this. This is not a geometric or a p-series. Everything we've done so far has been, all of our b of n's been these nice p-series or even a geometric series. This is, well, it's kind of a combination of both, right? So you can't really use either one. Don't forget, the very first test you should always try for everything. Let's look at a divergence, which is also called the nth term test. The divergence test, if you recall, simply says if I take the limit as n goes to infinity of my series, And as long as that limit does not equal 0, it diverges. Well, all right. You can L'Hopital this a couple times. You'd have to do it twice. And you can see if you L'Hopital it twice, the denominator immediately goes down to just a constant. But the numerator will always have that n in it. Or you can remember the growth rate set of functions. And when we looked at those growth rates of various functions, we know anything to the n is always going to be grow much, much faster than a variable raised to a constant exponent. So either way you look at it, your numerator is growing much faster than your denominator. That's going to infinity, which is good. By the divergence test, it diverges because the limit is not equal to 0. Okay? So we had to pull in the divergence test to finish that. We now have our comparison function. All that work just to determine what's happening with b to the n. We're not done yet because we still don't know what's happening with a to the n. The only way to determine that is to actually do the comparing. Now we're going to compare. But again, we're going to compare. We're not even going to attempt the direct comparison test because trying to determine if n to the 2n divided by 4n cubed plus 1 is bigger or smaller than, it's just too much. It's not something that can be done easily. So the limit can actually be done easily. So we're going to do the limit. So sometimes the limit comparison test you use over direct comparison just because it's easier to do the actual comparison. All right, n to infinity. I'll start with my a sub n times 2 to the n over 4n cubed plus 1. Remember, I'm going to divide by b to the n, which means I'm going to multiply by the reciprocal of b to the n. That's n squared over 2 to the n. Oh, here's what's nice. My 2 to the n's cancel, right? Boom. And hopefully you can see where this is going by now. N goes to infinity. I have n times n squared. That's n cubed over 4 n cubed plus 1. And by now we know, again, you can L'Hopital it. 3n squared over 12n squared. L'Hopital it again. You will, no matter what you do, or you can use the understanding that since the exponents n cubed over an n cubed are the same, I just take the coefficients. No matter what you do, you find that limit is 1/4. 1/4 is a perfectly good limit because it is positive and finite, meaning, yeah, it's not 0 or less than 0, and it's not infinity. So that means that a sub n behaves exactly like b sub n. And since b sub n, we've already proved that one diverges, a sub n diverges by the limit comparison test and the divergence test. And again, you can write just that as long as you've had everything I have above. So as you get closer to prepping for this test, you want to pay attention to how much work I show on the videos so you have an idea of what you need to show to do your work. Okay, that's your limit comparison test, and that finishes 10.5, which are both the direct comparison test and the limit comparison test.